Hello. This video is going to be a direct continuation of the previous one, where we were plotting isotherms of pressure versus specific volume for pure water. This graph right here is the result of that video, and hopefully, if you're here, that means you've seen it and understand what happened, and so you're ready to continue with this problem. So today we're going to be looking at how to find the roots of each of these temperature curves. So we're going to start by looking at something called Cardano's method, which is a method for finding the roots of any cubic equation polynomial. So we have that right here on these notes that Mr. Carlos has graciously provided for us. So right here, Cardano's method is as follows. For the cubic equation, x cubed plus ax squared plus bx plus c is equal to 0, which is the standard form, with real or complex coefficients, either doesn't matter, we can calculate q and r, which are these values, a squared minus 3b over 9, and 2a cubed minus 9ab plus 27c all over 54. And depending on the relationship of the value between r and q, r squared being less than q cubed, we can determine right away whether a cubic polynomial expression has 3 roots or has only 1 and 2 imaginary roots. Now obviously, since we're working with real pressures and volumes that are described by the cubic equation of state transformed into terms of z, the compressibility factor that we found in the second video in this series, we know that these 3 numbers are going to be real numbers right here, and either, depending on where it is located on this isotherm graph, will either have 3 roots or a singular root. Now, what do these 3 versus 1 roots mean when we're talking about, pressure and specific volume? Well, as you can see from the graphs drawn right here, some of these have what's known as a van der Waals dip, where the pressure curve goes down before coming back up and returning, while some of these higher ones up here don't have this dip and proceed straight from positive infinity to approximately the area 0. Now, what this means is this is determined by its relation to the critical point. Temperature curves and specific pressures, of course, specific volumes above the critical point will not have this van der Waals dip and will only have 1 root, which is far off into the distance on the right. However, those below the critical point will have this van der Waals dip right here and have 3 roots. So we can actually determine whether or not a fluid is critical or subcritical depending on how many roots its cubic equation has. Now these roots also correspond to something in terms of this isotherm graph, because the phase envelope that we are going to draw in later in the 5th part of this series actually matches with the roots of these polynomial equations. The first smallest root corresponds to the transition from liquid into the intermediate phase where both are present, and the third root corresponds to the transition from the dual liquid and gaseous phases to just a pure vapor phase. And then, of course, the middle root is important mathematically for what we're going to be doing later with the Maxwell constructions, but is not necessarily relevant to any physical quantity. So, all that being aside, what we want to do, our objective today, is to calculate the specific volumes which correspond to the zeros, or the roots, of this cubic polynomial expression that we discovered in the second video. So, how do we do that? We're doing that using Cardano's method. So again, Cardano's method right here says we take a, b, and c, which are the coefficients for the standard cubic equation, calculate q and r, and then from there on calculate theta, and from then the roots. So we're going to start by defining a new function. We're going to call it cube underscore roots. And cube roots right there. So what do we want cube roots to do? Well, we want to take in those coefficients, as we said, a, b, and c. Some a, b, and c. It doesn't really matter what they are. And we want to calculate everything we need. And eventually we're going to return, we're just going to call these v roots for now. That will change and go away as we continue with our programming. But for now, we're going to return those v roots. Or that's what we're going to hope to do. So the first thing we're going to do following these instructions is calculate q and r. So the first thing we're going to need is q. Well, q is equal to a squared, right? A squared minus 3 times b. And all of that is going to be divided by 9. So close that in parentheses, divide it by 9, and there's our q. We're also going to calculate r, which is equal to 2a cubed, so 2 times parentheses a to the power of 3, and that's going to be minus 9 times a times b, so minus 9 times a times, oh, no, 9, not times a times b, plus 27 times c, 27 times c, and that whole thing is going to be divided by 54. So close that in parentheses as well, divided by 54. So now we have our Q and R. So the next step for Cardano's method is to check to figure out whether or not we'll have 3 roots or 1. And we can do that assuming they're real, which obviously when A, B, and C are real, which is our case, Q and R are going to be real. So we need to check to see if R squared is smaller than Q cubed. So to do that, we're just going to use a simple if statement and say if R to the power of 2, capital R, power of 2 is smaller than Q to the power of 3, that means we have 3 roots, and I'll also say this corresponds to below the critical temperature. What we're going to see is, well, first we're going to have to calculate theta, and then we can plug theta into 3 different equations along with Q and A in order to derive our 3 roots. So the first thing we have to do is calculate theta. So theta is equal to the arc cosine of R over the square root of Q cubed. So it's pretty easy. NP dot cosine.
Did you catch my mistake just now? I was supposed to put in an NP arc cosine function, but instead I typed NP cosine. This mistake was caught between videos 4 and 5, so thankfully this does not affect any of our future episodes, and despite our numbers being slightly off, it is not really noticeable in any way in this video. Thankfully, it was caught and fixed before we continued on to the graphics portion and graphing of the phase envelope in homework 5.
That's going to be of, it was R, right? R divided by, and that's Q to the 3rd power within a square root. So that as an exponent is written as 3 over 2, which we can just shortcut to Q to the power of 1.5, because 3 divided by 2 is 1.5, so that all works. So this is our theta, and the next thing we're going to do is we're going to want to find these 3 roots. Now, looking at these 3 different root equations, we see they're very similar. It's negative 2 times square root of Q times the cosine of theta over 3, theta plus 2 pi over 3, and theta minus 2 pi over 3, and all of those are subtracted from 3a. So instead of rewriting this equation, x1 is equal to this, x2 is equal to this, x3 is equal to this, we're going to shortcut it a bit because of the way we can use arrays, especially with the NP addition, to make sure we can do it in a single line of code. So what we're going to do is we're going to set it equal to something we're going to call these just the roots, I guess. Roots are going to be equal to, well, those equations right there. So it's negative 2 times Q to the 1/2 power, square root of Q. That's going to be, yep, times NP dot cosine. So cosine of each of these 3 are different, so we'll leave it blank for now, and then we'll just subtract a divided by 3. So what exactly can we put into this cosine so that what we get out is all 3 roots? Well, we know from how NP handles NP arrays that if we put an array into an NP function, it will not iteratively, but it will go through and apply that function to each value in that array. So instead of rewriting this function each time for each root, we can instead plug an array into this NP function, and we will receive an array that contains all 3 values having been cosigned. So the first thing we're going to need in this array is going to be theta over 3. So this array is going to be theta over 3, the first item in our array. The second root is theta plus 2 pi over 3. So theta plus, since this is plus, we're going to have to put it in parentheses. So inset parentheses, theta plus NP dot pi. We're going to have to multiply that by 2. So 2 times pi. So theta plus 2 pi divided by 3. That's our second one. And the third one is exactly the same thing, but subtracted. So theta times 2 times pi, but it is minus, not multiplied, minus NP2 pi. We'll put spaces in there for clarity too. Minus 2 pi divided by 3. So that's our array with our first root right there, our second root, and our third root. all contained right here. However, when we eventually use these in our Maxwell constructions later on, we're going to need to have those in a correct order from smallest on the left to largest on the right. That way, when we program it in, we're not having to scramble to figure out which root we put where to make sure all our integrals actually make sense with what we're trying to do on the graph. So an easy way to do this is to actually use a function called np.sort, which when you put an array like our roots array into, it will sort them in order of smallest on the left to largest on the right and return an array of all those values sorted. So now that this is sorted, we'll have all three of our roots returned in the correct order from largest to smallest, and that's all we want from this function. So we can actually just return this, return right here. So that begs the question, well, if we're returning this here, we don't really need that anymore. So our function's done, right? Wrong. Remember, we're still within an if statement right now. This if statement is true only if r squared is smaller than q cubed, which only applies below the critical temperature. So we have to make an else statement, not that, else statement, that describes what happens when we're, at or above the critical temperature. So when we're at or above the critical temperature, what do? Well, Cardano's method thankfully explains what to do in that case as well. We can skip this since we know we have all real numbers involved. So if q and r are both real, we can actually figure out our single root by finding a, which is the negative sign of r. The sign function takes the number you plug in this case r, and says if r is positive, output a positive 1. If r is negative, output a negative 1. So essentially tell us the sign of the value, and then this negative is obviously going to do the inverse of that. And multiply the sign of r, the negative sign of r, by the cube root of absolute value of r plus r squared minus q cubed, all within a square root. Then taking a, determine what b is, which is q divided by a for all numbers except a being equal to 0. And if a is 0, b is also going to be equal to 0. And then finally, we can actually find our single real root right here, which is just going to be equal to a plus b minus lowercase a over 3. And these are our two imaginary roots. But since we're dealing with real applications that aren't electricity, we don't really need to worry about those imaginary roots because we can't plot them. So all we have to do now, since we again know q and r are both real, we can just type this in. So we're going to do a is equal to negative. Now we use np.sign, which is the np version of the sign function we just talked about, r times, and that's going to be a huge messy parenthesis right there. So it's going to be the sign of all of this to the 1/3 power. So we'll say it's going to be something else in parentheses to the power of 1/3. But again, we're going to have to encapsulate 1/3 as well because that's a fraction. We want to make sure it divides that before it does the exponent. Give it space there so it'll be easier to see. So it's something to the 1/3 power, and that's going to be the absolute value of r. So in here we're going to have np.abs of r plus the square root of r squared minus q cubed. So parentheses r to the power of 2 minus q to the power of 3. Let's double check, make sure that's correct. R squared minus q cubed. And all of that is to the 0.5, the 1/2 square root power. Again, not the square root power, but 1/2 power, which is equivalent to the square root. So everything is written out, I believe. Hit enter. So that tells us our a. So now we have to figure out what b is. So b is q over a if a is not 0. If a is 0, b is 0. So we could write another if-then statement like we did right here for our determining if we're above or below the critical temperature. However, since this is such an easy if statement, we can actually write it in a single line using something called a ternary if statement, or tertiary. Ternary doesn't really matter. The ternary if statement is actually written in this way. So we set b equal to 0 if, not is, if a is equal to 0. So this is our way of saying if b is equal to 0, if a is equal to 0, set b equal to 0. However, we also want to say if it's not equal to 0, we want it to be q divided by a. So we say else q divided by a. So we don't reassign b, we say b is equal to 0 if a is equal to 0. Otherwise, in the other case, set b equal to q over a. So that's our b taken care of right there. So now all we have to do is calculate our singular root. So our root is going to be a plus b minus a over 3. So we can just return this straight away as well. Return, this is a plus b minus lowercase a over 3. And everything should match up. So if we back out of here and close this should have no errors. Yes, that's wonderful. So we're going to just run a little test. This is going to be pretty easy. So if we run a cube root of something, and we say that a is equal to 0, b is equal to 0, and c is equal to 0, which would correspond to the cubic equation x cubed is equal to 0, we would expect our one root to be 0, because, well, for what number in x cubed do you get 0? Well, the only number that's when cubed gives you 0 is going to be 0. So if we run cube roots, we should get 0 out, and we do, which means everything is working, hopefully, as intended. So now that we have this formula to calculate the cube roots of any cubic polynomial, what are we going to do with that? Well, obviously, we want to use it in the case for our compressibility factor represented version of the cubic equation of state written out in polynomial standard form. So we're going to make a new function to do just that. So we want to define a new function that we're going to call cubic v that is going to eventually return our v roots. So how do we do that? Well, the first thing we're going to do is we're going to have to input the information required to actually calculate this. So again, this is all based off of an isotherm graph, a specific one singular plot for a specific temperature. And we're also going to need to know the pressure that this is all taking place at, because again, this is all based off the cubic equation of state. So we're going to have to import those values, P and T. And as well, because we're using the cubic equation of state, which again has different coefficients depending on which version of it you use, we're also going to have to include the equation of state, which we're going to set the default to SRK as per usual. So these are our three inputs. So now, having gotten those, we can actually, figure out what cubic v's solve this polynomial. So what we're going to do is we're going to run our cube roots function that we've just defined, but we're going to run through the coefficients that we derived from the cubic equation of state in terms of the compressibility factor, which we found in the second video. So we're going to write cube roots of, well, what exactly are we going to plug in? Well, I'll pull it up on the screen right now. It'll slowly fade in all nice and light. There's that handsome devil next to that start equation, and that right there is our cubic equation of state. Z cubed plus epsilon beta plus sigma beta minus 1 times z squared, so that's our first A coefficient. Then our second coefficient is B, epsilon sigma beta squared minus epsilon beta squared minus sigma beta squared minus epsilon beta minus sigma beta plus q beta, all times z, so that's going to be our B coefficient. And then finally our constant is q beta squared minus epsilon sigma beta cubed minus epsilon sigma beta squared. So those are our three functions. So all we have to do now is type those in. So we have for A, I have it pulled up on my second screen so I can actually see it as I type. We have epsilon times, I'll put a space there to make it more legible, epsilon times beta plus sigma times beta times, minus beta minus 1. So that's our first one right there. That's our A coefficient. Next we're going to input our B coefficient, which is epsilon times sigma times beta, S times beta, all squared, not all squared, but beta is squared, and that is minus epsilon times beta squared minus sigma times beta squared, and then we have minus epsilon times beta minus sigma times beta, and finally plus q times beta. So that's going to be our second coefficient right there for B. And finally we have our coefficient for z, which is our constant. So we're going to have,
the term I am about to type is supposed to be negative q times beta squared. I am going to write positive q times beta squared. This mistake was caught during the filming of our 5th video in this series, and was mentioned during our 2nd video, which was the derivation.
Q times beta squared minus epsilon times sigma times beta cubed minus epsilon times sigma times beta squared. So scoot over our parentheses so that it closes nice and neatly. And you can see right here we have our equation of state in terms of the compressibility factor z in our cube roots equation, which should hopefully spit out the 3 values of z for which are equal to 0, or in other words, are the roots of our equation. Now, obviously, you see a bunch of red lines because all this stuff isn't defined. So right now, everything is E and S are saying they're defined because earlier, way up here when we were running, we tested our A, B, E, and S function. So right now, globally, in this whole global Python collaboratory sheet, those functions are defined. However, within this function, they won't be. So we're going to want to redefine all of those. And how do we do that? Well, we can pull up those dictionary definitions for E and S that we had earlier. Or since we've already written a function to do that, we don't have to worry about it. We can simply do A, B, E, and S all equal to the function A, B, E, and S. And remember, that takes a temperature in our equation of state, which we're already pulling into our cubic formula. So temperature and equation of state right there. So now this is going to calculate our A and B and our epsilon and our sigma values depending on whatever temperature and equation of state we're using in the cubic V formula. That's perfect. So that's epsilon and sigma. We made sure they're defined, so even if you don't define them globally outside of the function, they are definitely going to be assigned and the correct epsilon and sigma for the pressure and temperature that you're looking at. So the next thing we want to do is say, well, what is beta and what is Q? We have to define those. Or if we remember back to that 2nd video I was talking about earlier where we actually derived the cubic equation for the cubic equation of state in in standard form, we actually used Q and beta as shorthand for other sets of terms. So we remember that beta is equal to B times P divided by R times P. Remember those on the bottom of all those super messy actions. And we also defined Q as A, which is that attractive factor, which in and of itself is dependent on T and a whole bunch of other things, but that's all taken care of in our ABES formula, times, I believe it was it? I think it was just A divided by, that was divided by B times R times T. And now we can be sure this is going to work because remember when we did in the derivation, we had Q and beta multiplied by each other to have A times P over R squared P squared because that canceled out a lot of the constants we had hanging around. And if we check that right here that Q and beta are correct by cross multiplying, we get the B's on the top and bottom cancel out, and we get AP over R squared P squared. So our beta and our Q are defined correctly. So that's wonderful. And so now we see all these squiggly lines are gone. So what we have right now is everything up to this point correct. So if we were to just run this function right now, besides the fact that vroots isn't actually defined, all this would do is it would do the calculation and it wouldn't really do anything with the results. So what we're going to want to do is we're going to want to assign something to that, obviously. We're going to want to call it z array is equal to cube roots, and we'll tab these over as well to make it look nice. I did not want to do that. That's not what I want to do. I want to put a space there so they all line up. There we go. So again, remember that this equation right here, this cubic equation that represents, or that's a derived form of the cubic equation of state, is in terms of z, the compressibility factor. So what roots pop out will be the compressibility factors that give us roots of the equation. However, we don't care what compressibility factor, because that doesn't really matter. What we care about is the specific volume that will give us those roots. So how do we get the specific volume from the compressibility factor? Well, if we recall that z is actually equal to PV over RT, because remember that z is always equal to 1, the compressibility factor is always 1 for an ideal gas, we can simply just do some very, very basic algebraic manipulation and realize that V is equal to ZRT over P, right? You take both sides and multiply it by RT to cancel out the bottom of the fraction, and then you divide both sides by P to get V all by itself. So instead of using V roots, we can actually just return the Z array multiplied by R, multiplied by T, which again is something we pulled in through the cubic V formula, and divide that all by P. Now, this is the reason why we needed the pressure right here, because in order to go from Z to V, we need to know the pressure of the formula. So, all that being said, this should not return an error, hopefully, and there we go. So now we're going to test it to make sure everything works nice and fine. We'll look up at our graph for inspiration of something below and above the critical point to make sure that it's working as intended. So the first one we're going to do is we're going to pick 425 Kelvin. That is very clearly below that. And our pressure is somewhere in negative 150 million Zim. So we're going to run that. So we'll try cubic underscore V. And we're going to run that with a pressure of around negative 150 million, okay, negative 150 e to the 6. Our temperature is going to be 425 in Kelvin, and our equation is SRK. So if we run this, yep, we get 3 roots, because again, this right here, 425, is below the critical temperature, and it has that van der Waals dip that we expect to see of an isotherm curve below the critical point. However, up here, these very clearly are above the critical point, because we can see there is no van der Waals dip, and 700 Kelvin is quite warm. So right here we have 700 Kelvin at 72 million in pressure. So all we're going to do is we're going to check cubic V. This time it's going to be, what did I say it was? Was it around 7 million for 700? Yeah, it doesn't really matter. We'll check up here. So we'll do 100 million. Nice round number. We'll do 100 e to the 6, and we'll have it at a temperature of 700 Kelvin, and hopefully this should give us 1 root. And it does. So this is perfect. We know that this right here is above the critical point, and it's giving us a single root, which is what we would expect. And this right here, this set of state, is below the critical point, and it gives us 3 roots. So everything's working as intended, and this cubic V equation absolutely works to give us the specific volume for which we experience the root of the cubic equation of state. So, another successful mission.